many ways where can we work around. So how to hack around these limitations? And there are plenty of possibilities. The first, change the hardware, of course. Intel and recently AMD both thought this would be a good idea, like many other processor architectures have this already. I mean, this 17 instructions, this isn't something by design because it's sophisticated or complicated. They just didn't thought about it. Okay, if you can change the hardware, you can emulate the hardware. You can do dynamic recompilation of the code you are currently running or supposed to run. You can binary rewrite the code, also very dirty and often used in virtualization techniques. Of course, you can port the kernel, stuff like user mode Linux does this. Or if you can't port the kernel or port the API because you don't have the source, you can try to emulate the API. There are some approaches using a microkernel, and last but not least, power virtualization and fractional kernel porting. So this is basically the techniques this talk is about. We are gonna talk about all of these techniques, yeah, all of these techniques. And but before we come to the funny and dirty part of it, we want to have another look at what virtualization monitor, or sometimes you call it hypervisor, depending on the implementation, should do for us. So first thing is protection management. Of course, it's important to seal the virtual and the physical architecture, and also important preventing virtual machines from interfering with each other or the monitor. Sounds reasonable. Of course, they don't have to know from each other. Another part of a machine monitor is resource management. I mean, giving a equal share of CPU, of network, of disk bandwidth. In case of CPU, network, and disk bandwidth, you just time multiplex. A space multiplex example is, of course, the memory. You need some paging support because probably the operating system wants to page non-used application memory out of memory. So you should support this too. Of course, virtualization gives us some things nearly for free. You can save a state of a currently running machine. You can recover the state at any other time, and you can migrate it to other machines. This is something that comes for free if you do virtualization. This is quite good. And of course, near to native speed. As I was looking through some implementation papers of virtualization on the x86, I discovered that all virtualization guys are Quake players. So it has to be near native speed. Well, to reach near native speed, machine monitor should at least, I mean, this is just a trailer, something like, you need at least fast monitor calls, means if something happens, you want to access the hardware from a virtual machine, you call the hypervisor. This happens quite often, so you need fast calls there. Also, you need fast interrupt handling. Every operating system has some idle instructions. You need to support this also. And of course, chunk writes for I/O would be quite satisfying in case you need near-to-native speed. Coming back to the Quake playing, this is from Denali, from a technical implementation PDF from Denali, one virtual machine monitor from for the x86. And you see, they already measured how many virtual machines of Quake 2, in this case servers, and the throughput they have. Well, 3 years later, there was Quake 3, and this is another virtualization monitor. This is Xen, and of course, the Xen guys are always doing the same. They are also looking if they migrate a Quake 3 server in while running, how long would be the downtime, and would this be acceptable for a Quake player? I think 50 milliseconds would be quite good. So virtualization helps playing Quake. Okay, but let's have a look at the techniques. First technique is, okay, the hardware change. Some people have made their thoughts about it. So the possibilities are just to change the 17 privileged instruction to trap into user mode and change a little bit of the semantics. Well, would be good because would be easy to implement if used as a switchable extension, also safe with legacy software. The bad thing about this, it's easy to implement. So, well, I don't know if somebody has tried, but I don't think you can't make a patent on bug fixes. So, of course, you invent a new set of instructions and a new mode, and then you can make your new patent. So, basically, it would be sufficient to fix these 17 instructions and everything would be all right. But in case of reality, we need something different. Intel VTX and AMD Pacifica, probably for those who don't know, are extensions of the x86 architecture to work around the limitations of the x86 architecture. And if you have a look at the design papers, I had a look at it, it's quite terrific and complicated. But of course, it does what it should do. So, Intel is shipping their new processors with this feature already, mainly in the server CPUs, but would take 1 or 2 years, and I think it would be mainstream. Okay, but we don't want to wait 2 years. So, what else can we do? If we have a look at full emulation, full emulation has its good side and its bad side. Usually the bad side of full emulation is it's slow. The good side, you can run whatever box on whatever box. Means you can run your Amiga operating system. You can run Windows on top of Linux. It doesn't matter. You virtualize every single piece of hardware, and as you see here, you're fetching some instructions, you translate them, and you execute every single opcode after thinking, what should I do with it? And then you update the virtual machine. It definitely has its good points. Box is one example of full emulation, virtualization. Of course, you have very good debugging capabilities for this. The other thing is you need to write a lot of code, because you need to write a BIOS, you need to write every single I/O device you want to support. But of course, Box is open source, and thanks to Box, many hybrid techniques of virtualization are only usable because Box has made the beginning and wrote many I/O and BIOS stuff. We will see this stuff in many other products. So full emulation is always a good thing if you want to try out something, but it's slow. Dynamic scan before execute, binary rewriting. If you look at the slide, there's something I want to tell you. Don't try to use LaTeX Beamer to make very graphical slides. You fail. So basically, that's what I try to do. But now let's have a look at binary rewriting. Binary rewriting is a funny technique, because you write into the code while it's running. I mean, that's fantastic. Yeah, it's not like database programming or real-time programming, where you do something very precise. Now, here you do dirty tricks and dirty changing opcodes while the system is running. Actually, you work around the 17 instructions again. But to work around the 17 instructions, first you must find them. Once you've found them, you put a breakpoint exception into it. This is just a 1-byte opcode, so that's quite easy. If you're trapped there, you know, okay, I'm here. That should be, I remember that should be that instruction. So I emulate these instructions and jump back. But you also have to take care about branches. So you must walk, of course, while it's running. I mean, while it is running in parts of it. Walk through the instruction opcodes, look for branches, mark these branches. If the code jumps into the other side of the branch, okay, you have to rewrite and look again what has happened. Do I need to examine another code segment, or is it just as we expected? So basically you do don't even think about self-modifying code. It's terrible with binary rewriting. But binary rewriting was one of the first techniques used